It is the second part of section 6.4. Here we'll study ridge regression and LASSO, which are regularization techniques. Ridge regression, also known as Tikhonov regularization, is with LT norm based penalty term, while LASSO is with error norm based penalty term. Here we have observation. When an LP penalty term is added to the original cost function, then it is now formulated in this way. Here, RP is just P norm of the weight. Such regularization can be considered as adding a penalty term to the cost function to encourage smaller weights. By increasing the regularization strength lambda, we can shrink the weight toward zero. It's quite natural to consider it. Here, once lambda is large, then here in optimization process will focus on the weight itself, so that in minimization the W, once the W is smaller, then now the minimization can be achieved. For example, lambda is extremely large, so that Q is ignored. Then now here in minimization, when W is 0, then it is minimized. So using large strength lambda, we can get smaller weights. For that object function, new object function with lambda appropriately chosen, the minimizer W star must be the point where the LP ball intersects with the minimum valued contour of the unpenalized original cost function. Here, pictorially, okay, now that is original cost function, and this is contour plot, and this is original minimum. Now, that is from penalty term. Then here, once we are making again contour plot, then the minimizer must be pointed such that this one is intersecting, that circle is intersecting to that curve. The reason is lambda is a kind of Lagrange multiplier, and then now the gradient of that, the contour, and then gradient of this, the level curves should be parallel each other, so that once the minimizer is happening, then at the point here, the gradient of the original the cost function and gradient of this penalty term should be parallel, so that they are intersecting each other. Okay, for this is for L2 norm, L2 regularization, but right side is for L1 regularization. Now, in error norm, the error ball is like here, diamond shape or rectangular shape, and side is straight. So once it is happening, then here, now, because it should be parallel, the gradient must be parallel, so that the minimizer will happen in this picture at this point. Okay, that is observation. Here, LASSO, the right side here, L1 regularization. in the right figure, Aaron ball touches the minimum valued contour of the cost function at W1 equals 0, which means that the optimal solution, minimizer W hat, will have the 0 first component. W1 must be 0. Right? So that means that now, which encourages sparsity. And if we generalize this idea, then now for some component in W can be 0 or small around the 0, so that here that is now the same effect as the eliminating the corresponding features, right? So it can serve as feature selection method. Here, LASSO, L1 regularization, we can enforce sparsity by increasing the regularization strength of lambda. A sparse model is a model where many of weights are 0 or close to 0. Therefore, L1 regularization is more suitable to create desired 0 weights, particularly for sparse models. Here we have another remark for the general regularization techniques. In general, regularization can be understood as adding bias and preferring a simpler model to reduce the variance overfitting, particularly when number of training data set, the size of training data set is small. Error regularization encourages sparsity, as you can see this picture, where W1 must be 0. That means that the first feature column is ignored, so it's eliminated. Right? And we can enforce sparsity by increasing the regularization strength lambda. We already considered that. Thus, it can reduce overfitting, serving as a feature selection method. However, L1 regularization may introduce oscillation, particularly when the regularization strength lambda is large. A post-processing operation may be needed to take into account oscillatory behavior of L1 regularization. We'll see an example here. Consider a model consisting of the weight N, now R1 and R2. R1 is L1 norm regularization term, and R2 is L2 norm penalty term, regularization term. Now, we may assume that here this is an objective function, and also is another objective function. Now, to see the effect of this penalty term, we momentarily ignore the original cost function. Then now we are applying gradient descent method. Here for R1, the gradient is sine of W. That means that weight is positive, then the derivative will be 1. Weight is negative, then derivative will be minus 1. And once it is 0, then the 0. For R2, is gradient is definitely W. So that if we are using gradient descent method, then for R1, the object function R1, the next one is updated from current weight minus lambda, the gradient of R1, which is sine WK. So that is the update for R1. For R2, now the gradient is W, so that we can rewrite in this way. And then Now, if you go down to W0, then the initialization, then we can see this one. Lambda is usually less than 1 and positive number so that it is approaching 0. So here for L2 gradient, that is now linearly decreasing towards 0, as you can see here. So L2 regularization will move the any weight towards 0. But later on, it becomes smaller and smaller. But anyway, it's moving towards 0. On the other hand, L1 regularization will move any weight towards 0 with the same step size lambda. Always the same step size, because sign will be 1 or minus 1 and 0, so that it is always the same step size. So for example, here we consider this oscillatory example. Start with W0, 0.2, and assume we choose lambda is 0.5. Then W1 will be now 0.2 minus 0.5, and the sign of W0 is 1, so that here 0.2 minus 0.5 times 1, which makes minus 0.3. And start with a minus 0.3, the next iterate will become 0.2, because now sign is minus 1, so that minus 0.3 and minus 0.5 times minus 1, which will be 0.2. So that here, start from 0.2, it becomes in next iterate minus 0.3, and again becomes 0.2, and again minus 0.3. So it's endless oscillation. In reality, this oscillative phenomenon may not be severe because the R1 is used as a penalty term for cost function. The R1 is not all. In fact, there is original cost function. So with the combination, this oscillation is not so severe. However, once you choose large lambda, then we may need post-processing to take care of that oscillation. Okay, that's the end of the section. Thank you.